Alright, hell yeah. So this video is going to be about partial derivatives, and then also someone's like, hey, can you do a video about mathematics? And so we're going to kind of talk about mathematics as we go along as well, because mathematics is kind of a form of logic that, I mean, if you follow all the parameters, you can't mess up. But we're going to show, today I'm going to make a mistake somewhere. And so, and then we're going to figure out how we also use, oh damn it. Alright, so we're going to also use, like as much math as we can, kind of from throw it into our calculator, use graphs, and just so we can catch those errors. Okay, so we have a spider and a fly, and I forgot to rearrange these pictures, but I'm going to go from here to the fly is going to go to the spider for whatever. I should switch these around, but anyway. I just chose to go here, and then we're going to try to go to the fastest route. And I've already made kind of a video on this where we go down, and this fly is going to be a distance of 1 up. So we could go down 1 over 100 and then up 9. That's going to be a distance of 110. So then the question was like, well, could we go, is there any other better way to go? You know what I mean? Could we even just go to this halfway point, go down 1, come over here to this halfway, and then maybe hit this point right there, go over, and then down. You know what I mean? Like, let's say, let's try that one. So that would, but then when it comes to mathematics, then we, the first thing that we're going to come into is Pythagorean's theorem. And I mean, do you trust that? Do you trust that if this side of this triangle is 50, this side is 5, that we can just square these and add them? And once we square them and add them, that's going to be this length squared. You know what I mean? So, so this hypotenuse is going to be the square root of 5 squared plus 50 squared. I mean, do you trust that? So that's the other thing about mathematics is it's good to also go back and take these concepts, like even like the Pythagorean's theorem, and play around with it. From a proof. You should always do proofs, but sometimes even just playing around, with the triangle. And changing it and just seeing that pattern emerge is kind of proof enough. Okay, so moving on, now we're going to get this triangle. It's going to be 50 and 10. So we're going to do that same thing. So we have the square root of 50 squared, and I'm going to add it to this distance we already did. So we're going to do the square root of 50 squared plus 10 squared. Whoa. Sorry about that. And so now we have a total distance of 101. Now we're to here, so now let's go 5 and 1, so that's going to be 6, and then we're going to go up, and then we still had to go this down. So we went 1 over, we had those hypotenuses, we added those, and then we went 5 and then 1. And we get a distance of 108. Well, sweet. So then the second thing is like, well, if I come down to this midpoint, go halfway, go up to this corner, why not just go across? Isn't that going to be a lot better? And so, hell yeah. So it's going to be the same two hypotenuses there. We're going to have 1 right here. But now this, we're going to add another hypotenuse. This is going to be 1, 5 triangle. So we're going to have 5 squared plus 1 squared. Cool. And we get a little bit better, 1.73. And so we did this process. And then, maybe just by logic of saying, hey, if these are going to be in the same location, it seems like whatever we did down here, we should probably do up here. So down here, I went straight here, and then I went across to this midpoint. You know what I mean? So it's kind of fascinating. I want to do this one just to see if I hit this midpoint, go straight up. I bet you that's going to be worse. That for sure looks worse. But let's try it. So we're going to have... we're going to go 1 on both sides, so that's going to be 2, plus, and then we're going to have this hypotenuse, but we're going to have 2 of those, because we have the same. So we have the square root of 5 squared plus 50 squared. And then we're going to just go up 10. And no, so that was worse, but it's just fascinating that had we gone, there's a point where if we go this direction and hit some sort of midpoint and do that same thing over here and then go up, like that's going to be the best. And so in the previous video, we found that that was pretty close to about, if this is halfway, it was pretty close to about 25. And actually, if we just go straight down here and go to this quarter distance at 25, then go up here, and this is 25, then that was like really pretty accurate. And then the other thing was we talked about how, well, is it beneficial to go straight down, or is it beneficial to come at an angle? And so even just right there from geometry, would it be beneficial to go that way and then come over here? No, that looks longer. But so then in the other video, we just decided to, hey, take a small little increment this way and see if that improved our scenario. And it did. Okay, so then we got into you know, setting this up as an equation. So that's what we're going to do right now. All right, hell yeah. So if this is the perpendicular straight down, we're going to come out here. We're going to call that distance x. Here's the halfway point. We know we're going to mirror our image, so we definitely have to go through kind of this halfway. We're going to hit this side. I'm going to call this a distance y. And we know the dimensions of the box. So this is the midpoint. If I'm calling this x, this distance right here is 5 minus x. Same thing here. If I call this y, and we'll get to this in a moment. I mean, this distance right here is just, you know, 50 minus y. Cool. And then we'll do the same thing over here. We're going to come in at a distance x. We're going to hit this at a distance y. This is going to be 5 minus x. And then these 2 points are going to meet. And sorry, the middle's not visually very good. But anyway, and then so this distance right here, if this is y and this is halfway, this is going to be 50 minus y. Or we could say this whole distance right here is going to be, if this is y and this is y, and the full distance is 100, this is going to be 100 minus 2y. And that's kind of what I use in my equations. So now we can get an equation for the distance from here all the way up to, you know, from the fly to the spider. And it involves using x and y. So we have 2 variables there. So let's write that equation. So the length, and I guess if you writ this, you know, it's going to be the length, and then the variables that we're changing are x and y. And this is kind of interesting because this video I'm not going to go into it, but why not make the box have sides A, B, and C? You know what I mean? So then my length would be a function of A, B, C, x, and y. So that's the other thing when, you know, talking about mathematics is a lot of things are just like, hey, this is just a function of x. We have like x squared. You know, we just have one thing going on, but you could have, you could say, hey, this is my income, and for whatever reason, someone's paying me like an x squared salary. Every day, I'm going to get, you know, on the first day, I'm going to get $1. On the second day, I'm going to get $4. And on the third day, I'm going to get $9. That's pretty nice getting paid, but maybe they're just going to pay me that for a week, so it's not that good of a deal. But if this is my income, maybe I have 2 jobs, and the other job is pretty sweet. It actually pays me with this equation, y cubed. So on the first day, I still make $1. On the second day, I make $8 bucks. And then on the fourth day, I make, I'm really bad at this. So it would be 4 times 4, that's 16 times 4. That's going to be 64. I'd make $64. And did we do the 2 right? 2 times 2 is 4 times 2 is 8. Hell yeah. So yeah, this job's sweet, but I'm only going to work for a weekend. You know what I mean? So now, and let's say this is just like a Friday, Saturday, Sunday commitment on these 2 jobs. And now my total income, let's say, is going to, well, it's not going to be just a function of x. My total income is now a function of x and y. But this is where mathematics sucks, because they just use these general terms like, hey, this is a function. And it's just like, I don't know. Like, no, this is the money you're making. You know what I mean? And that's going to be x, y. And it has these 2 variables. And so, and then we have x squared plus y squared. Cool. And And then it's kind of interesting, it's just like there's nothing to optimize here. You know what I mean? Like, obviously, on the third day, we're going to have the most money. You know what I mean? There's nothing about this equation. It's just going in one direction, and it's going pretty fast in that direction. But this equation is kind of interesting, because if we change x and y, and that's the other thing about math is like, or what we talked about is like, well, if I'm setting this to be x, like what's a value x could be? Well, if this is the midpoint between this side, x could be 0 or it could be 5. So cool. So just keep that in mind as well, because like x can be, 0 to 5. And then y could be, well, we could just go straight here, y could be 0, or we could go all the way to 50, and we did that scenario where we go straight up. And we're trying to have, we're doing the same thing equally on both sides. So yeah, it would only make sense if y was 0 to 50. All right. And so cool. So we get this equation for length as a function of x and y. And I guess I'm just going to write it down here just so we can hopefully get it all in one go. Okay, so this hypotenuse is going to be the square root of 1 squared plus x squared. Cool. I guess we don't have to, this isn't going to get too out of control, because we're doing the same thing up here as we're doing right here. So we're going to have 2 of those. Cool. And now this hypotenuse is going to be, and we're going to have 2 of those. So we have 2 square roots of 5 minus x squared plus y squared. Alright, hell yeah. And then right here we just have 1 hypotenuse. And so that's going to be the square root of 100 minus 2y squared plus, and this is 10, plus 10 squared. Alright, hell yeah. So we're done. And now what I'm going to do is we're going to write the differential equations for this. And man, maybe I should get a second sheet of paper to go through that. Alright, hell yeah. So now we have our equation, and we have 2 variables. And the differential equation will tell us if we well, it's going to give us an equation. So if we take this equation and we take the partial derivative of this equation xy with respect to x, this is going to tell us how much this length is going to change as we change x. But it's going to give us equation like something something x, and then we get to put x in. So if I say x is 0, it's going to tell me kind of the amount of change, and because it's going to just pop out a number, this is kind of interesting, you have to kind of intuit that this number is still going to be a change in length divided by changing x. But then some of these problems, you're not going to be able to change. So this one, we're only going to be able to change. X is optimized when x is 0.196. So we can't even change x by a full value. And so, yeah, so kind of keep that in mind. But yeah, this equation, when we throw in x is equal to 0 in our partial differential equation, it's going to pop out a number that says, hell yeah, the change in length will go negative down, because we're going to be reducing this overall length. So let's say it's negative 0.4. So that's going to be the change that we're going to see. And so if this is, and I think that was fairly accurate. Okay, but then let's say we're really close to the optimal point. So if in this equation, if I throw in x is equal to 0.196, it's going to say, hey, the change is 0. It's going to say 0. So that means the change in length will be 0 at that location if I move one way or another. But it's kind of interesting, because your change in length isn't going to be 0 if you go from this point and go from 0.196 to 1.96. So that's kind of the interesting thing about how to read the output of kind of a differential equation. It says just at that very location, you know what I mean? So even though this number is going to be kind of in terms of like you're changing x of a full value, so if this was 0.4, negative point, so if we're at x is equal to 0, and we're going to change by negative 0.4 when we change x by 1, maybe, yeah, that's that's not going to be 100% true, because it's only going to be realistic if we change x just by a little bit. Maybe at 1/10 is a little bit. Let's say 1/100th is a little bit. So we're going to take this value and have a change in x of 0.0. This is going to be a change in length of -0.4 for a change in x of 1. So, but we're going to change our x by 0.01, and then so we're going to take this, and it's going to go 0.004. So now this is more accurate. If I change my x by a hundredth of a meter, then my change in length is going to change by that much. And then once I'm at that new location, I throw it in. Now this isn't -4 anymore. Maybe it's -3.95 even. You know what I mean? And then so I would do that same process. All right, so that's kind of in a nutshell the partial derivatives. All right, sweet. And then you're going to have two of them where we're going to take the partial derivative of this function, which is an xy function with respect to y. And then that's going to give us an equation if we adjust y. Then is that going to help us out? But we can only adjust one parameter at a time with these differential equations. There's not a setup where, you know, from this we can just instantly get an equation where we adjust both of them at the same time. Alright, hell yeah. And then when it comes to mathematics, there is kind of this hand-waving nature of differential equations. Just like when you're doing addition, 1 plus 2, you kind of know what's, you know the logic behind it, and you know like the fundamentals. But every part of math has that same kind of logic. If you follow the logic, then you know you can't go wrong. But with these differential equations, man, there's just plenty of places to make mistakes. So all right, let's dive in. So we have the partial derivative of this length xy with respect to x. We'll do that one first. Cool. And then so we're just going to use the power rule. Basically the power rule, and then you will do kind of you call it u substitution, but if you don't call it u substitution, I swear your brain doesn't get fried. But basically you just have to take the power rule, but then, and let's talk about this, because even if I do so if I have y is equal to x squared, I can do the power rule on this. So if I take dy, and always do this, when you're doing the derivatives, I don't know, do parentheses around this, because this is the change in the function, and then also do this. This is the change in this function y of x with just changing the value of x. You know, so sometimes just rewriting this a few different ways. You know, we're just going to take the derivative of this, and the derivative of this is just, you know, dy dx is just 2x. I think we all know that, but you can kind of do the power rule and the u substitution all in one go, just by changing the equation to this. You know, do parentheses x squared, and yeah, maybe what's inside the parentheses matter. So now we're going to take the derivative of this. Dy dx is going to be bring down the power, rewrite everything on the inside, take that to the, drop the power by 1, and then take the derivative of the inside, dy dx. Cool, and so then you have this, well, this fundamentally is just 1, so, you know what I mean? So that's kind of helpful. So even though, you know, for this, you probably won't use u substitution, you can, and I think those are some pretty good fundamentals. Alright, hell yeah. So now we can just go for it. So we're going to bring down this power. 1/2 times 2 is just 1. We're going to rewrite everything on the inside. It's going to be no longer a square root above in the numerator, so I just write parentheses 1 squared plus x squared. This was to the 1/2. We're going to drop that power to the -1/2. Okay, next one. The half, that power comes down, cancels the 2. We're going to have 5 minus x squared plus y squared to the -1/2. Okay, hell yeah. This power comes down. We will have it out here. Oh, holy hell. I totally forgot what the hell we're even doing. And yeah, that's the thing about differentiation. That was the first mistake I made. So anyway, so yeah, and I just went over it. You know what I mean? You have to take the derivative, you know, bring the power rule, take down the power, write the inside, and reduce the power by 1, and then take the derivative of the inside. So even if you just have one little variable here, hell yeah, you're going to do the same thing. Alright, so sorry about that. So we're going to bring down the power. That cancels. We're going to rewrite this. 1 squared plus x squared. And then bring down and then drop the power by a 1. So this becomes negative 1/2. Now we're going to have to multiply by the derivative of the inside. This is a constant, and the derivative, and we're still differentiating with respect to x, so it's kind of the same thing applies over here. You can just know this. Derivative of x squared is just 2x. Get on with life. Alright, next one. So we have plus, and then we have the half. Bring down that power. So we have the inside is 5 minus x squared plus y squared. Alright, to the negative 1/2. And now we're going to take the derivative of the inside. Now we are just differentiating with respect to x, so this just becomes a constant. There is no x here. And in the other video I kind of showed, and maybe we'll do that. So alright, so we're taking the derivative of the inside. We still have to have those same rules. Bring down the 2. Take this power to drop the power by 1, and take the derivative of the inside. Derivative of constant 0. Derivative of negative x is the same thing. Negatives and numbers out in front of this x can be, so the derivative of negative 2x dx is the same thing as, you can bring out the constant, so we have 2 derivative of negative x, that's the same. And we can totally see that this is kind of cool. Like, I'm doing this more in statics and stuff with vectors. Is like, hey, I can totally rewrite this as negative 1 times 2 times x. So sweet. So these are both constants, and then I can pull them outside. You know what I mean? So now I would have negative 1, 2, and then derivative of x with respect to x. Hell yeah. And we know that this is just 1, so then I'm just left with, in this case, just negative 2. So the same thing here, or you just, you can do that same process, but just see that taking the derivative of negative x is just negative 1, and we're done with that one. Now if I'm taking the derivative of this, it doesn't have x in it, but let's do that same process. We're going to bring down the 2, take y to the negative 1, and take the derivative of the inside. Derivative of the inside is y, so we're going to take dy with respect to x. But there is no x here, so this is, and yeah, I mean, this ain't a function, it's just a number, you know what I mean? So at the end of the day, that is just a number. And when we take the derivative of a number with respect to x, it's the derivative of a constant with respect to x, and that's 0. So, I don't know if that's 100% legit what I just said, but it just kind of emphasizes that, hey, that's a constant, the derivative of it is 0. Alright, booyah. So we're done with the inside there. Now that same process can be applied. You can bring down the power. We'd have 1/2. Take everything to the inside, to the negative half, and then multiply by the derivative of the inside. This is going to be 0. And then this. You're going to bring down 2. Then write the inside to the 1 power, and then still multiplying by the derivative of the inside. This is going to be 0, but we're going to have 0 plus the derivative of this. You can bring outside the constant, negative 2. But what's the derivative of y with respect to x when we just said y is a number? Well, that's going to be 0. So that whole thing, at the end of the day, you can do that. You can do all those processes, but you're still going to be multiplying by 0 right at the very end. So it treats, that's a very good visual way to see that, hey, that's a constant. But or you can just overlook this entire thing. If this is a constant, everything else is a constant. The derivative of this whole term is just 0. All right, hell yeah. So we got our derivative. This is our partial derivative of this length equation that has 2 variables, x and y. With respect to x, we did it. So now we're going to do the partial of this length equation. Has 2 variables, x, y, but we're going to take it with respect to y. Alright, so this has no y in it, so that's going to be a constant. This has y, that has y, so let's do that whole process. Bring down the half, that power, this 2 goes away, parentheses, 5 minus x squared plus y squared. To the negative half, we just drop the power, and then we multiply by the derivative of the inside. This is, we're differentiating with respect to y, So there is no y here. That's a constant. And then we just have 2y. Okay, hell yeah. All right, moving on. We have dropped the power. And there is no 2 here, so we are going to have a 1/2. 100 minus 2y squared plus 10. So I rewrite everything on the inside and then take it to the negative half power. Drop the power and then multiply by the derivative of the inside. This is a constant, that's 0. We do have a y here, so we're gonna have to treat this just like it's normal and bring down the 2, write the inside drop the power to the 1, and then take the derivative of the inside, which is negative 2. Hell yeah! So that's it, and I kind of rewrote. I've already done these before, so let's see if these match up. So we have 1, so this is just 1 plus x to the negative half, 2x. Check there. 5 minus x squared plus y squared to the negative 1/2, 2, 5 minus x, negative 1. And we'll get to a second why we set these equal to 0. But this is just an equation for that derivative. Alright, so the second one is 5 minus x squared plus y squared, all of that to the negative half, 2y, plus 1/2. We have 100 minus 2y squared plus 10 squared. All that to the negative half. Okay, we have 2 multiplied by 10 minus 2y times negative 2. Alright, so we're good to go there, and I got printouts of this. So this is kind of where we start to do our problem. And again, like, why do we set these equal to 0? Because if we know we're at the optimal point, there is no you can't change y to change the length. You know what I mean? So if we are at the shortest length, well, and that's kind of funky. But yes, this yeah, that's the thing. That's the hardest thing for me about differential equations, is just kind of this explanation of it. Because we just said that if we're at the optimal point and then we move one way or the other, hell yeah, our length increases. But at that very, very location, if we move just a tiny fraction, like left or right, this number, so let's say we do that. Let's say we're at the optimal location, and then we move just slightly away from that, just by like a thousandth of a meter. Hey, our overall change in length, it will change, but it's just going to be so minuscule. Compared to being at x equal to 0, and then we change a thousandth of a meter, hell yeah, that number is going to be substantial even, compared to at the optimal point. Alright, so that's one way to explain it. But anyway, so when you set these two differential equations, or partial differential equations, equal to 0, this is where you're going to be optimized. And in this equation, when we differentiate with respect to x, we were optimizing x. So, but for this, you have one y term. And so you just have to assume that that's going to be some sort of number. And then when you do, you're going to optimize x. For whatever value of y you choose, you can move x. See, this is the process where you can kind of only move one thing at a time. You know, I can set y to be whatever number, and then I can change x to be optimal. But maybe this y is not optimal, the y that I chose. So then I come down here, and then kind of the same thing in reverse. I have one value of x that I might choose, and then I can adjust y to be optimal. But who says that I chose the right value of x? So that's where if we put this equation into here, then that will be the right value of x. I mean, if I solve this equation for x and then jam it into there, then hell yeah, I'll have the right equation. I shouldn't say that. So that's the process that we're going to go through. Is the cool thing about this problem, and the quick solution is just, it's a straight line when you just unfold the box. Cool. I'm not going to go over that because I think that's a magic. I'm going to stay 10 miles away from that idea. Because this opens up the door to learn partial derivatives, and that's kind of cool. But at the end of the day, if you do unfold the box, you're going to have a straight line, and it's just going to have a Pythagorean's theorem. You're going to have dimensions, but you are going to have kind of where that straight line would cross those intersections of those panels, and those are going to give you your distances, your x and your y's and stuff like that. But those are just very, just from the Pythagorean theorem, those are very simple equations. So even though this is complex, we can solve it. So that's what we're going to do in this video. Alright, hell yeah. And this is why I like to stay on the idea of the topics of what's going on, because, I mean, you could just say, hey, I got a differential equation. When I set it equal to 0, I'm going to get a min or a max, and I just know from, from this problem statement that if I, if both these two equations are satisfied, that's going to give me the min. That's going to give me the minimum length. So at the end of the day, we just have two equations here. This equation and this equation, we set them equal to 0. We have two unknowns. We have x and y. And so we're going to go through the process of solving this one. And I didn't do it in the long video because yeah, we can get an actual equation for the number. I mean, we can get both numbers. We can basically get x as something just with numbers. Whole, integer numbers, and we can get y as an equation of whole integer numbers. We have to use the quadratic equation, and so we are going to have something like square root, plus something divided by something. So that's kind of the form of our equations that we're going to get. Okay, and sometimes partial differential equations are difficult to solve because there's so much going on, but we have a lot of x terms, but we only have one y term. So that's going to be my indicator. And I really didn't know going forward, but I was just like, but I did know it's just like, hell yeah, if I only have one y term, I was like, sweet, I can get everything to one side and just have y by itself. So from a mathematical perspective, it's like, that's totally legit. Even if it's hellaciously ugly over here, then I can still throw that, so I can have y is equal to this something gnarly, and I could, that something gnarly is going to have, x terms in it. So I have y is equal to all these something x's. And if I plug that equation for y into all these y's, this whole equation just becomes something x, and equal to 0. And then so I have one equation, one unknown, and if it is equal to 0, well, from that perspective, and that's where I kind of threw in the towel on the last one. I just throw it into my equation and just, say this is the y value 1 in my equation, and then everything else is a value of x, and then I can solve for x. And then once I solve for x, I can throw that x value into the other equation, and then do the same thing and solve for y. Alright, so, but let's do it. So we're going to do this equation first, and we're going to solve for y. So now, I guess, yeah, we'll probably kind of slow roll this. So we have, oh, but here's something that's kind of interesting. This is where I brought it up as going through this. I want to cancel as much stuff as possible. So when this is a negative, so I can just see that I can add this to the other side. If this is on the other side and this is the equal sign here, then I can, the second I get this to the other side with an equal, it's easy to see that I can cancel out the 2's. So I was just saying, it's like, well, why can't I see that prior to that? I have, so this would be like ax plus bx is equal, or I'm sorry, this would be like 2a plus 2b is equal to 0. Why can't I see that I can cancel out these 2's right now? You know what I mean? Because obviously I could get 2a is equal to negative 2b, and then I could divide both sides by 2, and I'm satisfied there. So, but I guess I'm always just cautious, or no, this is a mathematical thing that I don't visually see. If all the terms are on one side and I'm equal to 0, I guess, yeah, when something is equal to 0 on that side, it's like I feel like I need a term over there just to be like, okay, now I can cancel stuff from both sides. But hell yeah. Okay, so now moving on, we're going to say that this is x divided by the square root of 1 plus x squared. So now I'm bringing back the square root sign just so it's visible. And then I'm going to say this is equal. I got this to that side, and we have 5 minus x on top. On bottom, I have the square root of 5 minus x squared plus y squared. But alright, so now let's start the process of like not making mistakes, or making them and then finding where we made them. So we still have to get this y by itself, and so might as well get it up there in the numerator. So that's what we're going to do, and then we're going to get all these, I'm going to get this term up there and this x down there. Okay, hell yeah. So I have the square root of 5 minus x squared plus y squared is equal to 5 minus x square root of 1 plus x squared. And I think writing sloppy can be useful. Well, I have to write sloppy because my hand will just start hurting if I get too detailed. So just to let you know on that side. Okay, so we're still trying to isolate y. And the next thing we do is we square both. So we have to get rid of this square root. So we do that by just squaring both sides. And if we do that, we square that term, and hell yeah, this is a square root, so now that just kind of goes away. Okay, it looks like we just did that. So now I'm just going to do it like that. Okay, hell yeah. And especially kind of doing multiple steps. If you're just trying to chisel out the answer, there's no reason in writing too much. Still trying to isolate this y. So now we're going to subtract over here 5 minus x squared. And sorry, it's all... whoa. 5 minus x squared. Now we have this minus this. The only way we can kind of add fractions is if this... So let's rewrite this, I guess. So we have 5 minus x squared, 1 plus x squared divided by x squared. Now the only way I can add or subtract these fractions is if the denominator is x squared. If I put the denominator as x squared, I got to put the numerator as x squared. Because these are now just 1. So now I have minus x squared, 5 minus x squared divided by x squared. And sweet. So now that I can add these straight across, and even if you can't see it, well, let's do it in one step. So this, I can add these, because this is the other mathematical thing that I kind of like, is like, yeah, if you have a lot going on, just call things... It's the same thing as if I have 3 square roots of 2 plus 1 square root of 2. Like, how do I know that this is 4 square roots of 2? Sometimes that's very difficult. I use the idea of oranges. Be like, hey, if I just had 3 plus 1, you wouldn't bat an eye. It'd be 4. But just consider these like oranges. I have 3 oranges plus 1 oranges, especially when you got something funky. And that's just going to be 4 oranges. The other mathematical operator of this is that you can just factor that out. So we have square root 2, factor the hell that out, and we got 3 plus 1. So now we got square root 2, and then you got that something normal that you're used to. It's just 4. Alright, hell yeah, same thing here. So visually I can see, hell yeah, this is the orange, and I have 1 plus x squared oranges minus x squared oranges. Okay, hell yeah, let's write that. So I have... and that's all I'm doing is just saying same thing here. Factor this the hell out, and then I just have this multiplied by 1 plus x squared minus x squared. You know what I mean? So a lot of different ways to see that. Do I want to write that again? I mean... Yeah, obviously you would just, the easiest way is just to factor this out. Because yeah, it's not so obvious of like what 1 plus x squared oranges plus x squared oranges is just like, well, I can, or minus x squared oranges. But I mean, yeah, that still jives. I still have 1 plus x squared minus x squared oranges. 5 minus x squared. Cool. And if I have 1 plus x squared minus x squared, well, cool, I just have 1 orange. Oh, sweet, hell yeah. So there's just kind of a few different ways to look at that. Or just factor it the hell out, and we got 1 plus x squared minus x squared. Cool. Sometimes the negative sign can trip me up all the time, so just change it to a positive, and then put a -1 right here. That's the same thing. You're just adding, but then... you just have a -1. You know what I mean? If you had a... Yeah, so yeah, it's no big deal. And now you can do that same thing. So we would factor out the 5 minus x squared, and you're going to have 1 plus x squared plus negative 1 times x squared. Cool. So I think even that is just a little more visual to see. Probably not though, but yeah, any way that you're not going to make mistakes with those negatives is always finding good little habits. I haven't found the best habits, but I have, like, that's one that I kind of like sometimes. And so sweet. So so these cancel. X squared minus x squared. So we just have 1. So yeah, so this whole thing, this term just became 5 minus x squared divided by x squared. And I think we lost touch of reality of where the hell we even at. So we got this upstairs, this over there, this down. Took the squared every side. And then we subtracted this 5 minus x squared. And so now we just have y squared over here. And then we went to add these two fractions together. So we still have y squared is equal to this. So we had y squared is equal to adding those two fractions. We figured out how to add them with the orange method maybe. And now we have y squared is equal to this. Sweet. So we need to take the square root of both these. Square root of this is the square root of the top, square root of the bottom. So that's just y is equal to 5 minus x divided by x. So that's kind of cool that you can get a fairly decent, answer that's simple. Alright, sweet. So now we're going to do the same thing over here with this second equation. Alright, so I see that we can factor out that 2. We can just factor out one of these 2's. Oh, no, this is a half and this is a 2. So hell yeah, we can factor out this. Just make sure you don't lose this negative. So that's what I just did right. I just turned it into a negative 1 so it's obvious. I'm going to do that same process. We're going to do y and then do the square root downstairs. 5 minus x squared plus y squared. Alright, and this is going to be equal to, we got 100 minus 2y. This is in the numerator. This is a square root in the denominator. So we have 100 minus 2y squared plus 10 squared. Alright, hell yeah. And then in this, we had a lot of y's. But we only had one x. So we know that we can get everything to the other side. I mean, so, yeah, but this is in the denominator. It's just like, well, why can't you just get everything to the other side and then start, is because this is in the denominator. So it's kind of nice to do this format. And then make sure your x is in the numerator. So this is the only thing we're solving for. Everything else is in terms of y. So let's get this upstairs, this over there, and I'll even do it in that order. So we have y, get this up here, 100 minus 2y squared plus 10 squared. Okay, and then I'm going to get this downstairs. So we have 100 minus 2y. And then that's going to equal, now we get this upstairs, because we're trying to solve for this x term. So we have 5 minus x squared plus y squared. Okay, hell yeah. So now I'm going to square everything over here, and this thing goes away. So now this side is just going to be 5 minus x squared plus y squared. And this is going to be y squared. This square root goes away. But it's still multiplying. So even though that square root goes away, we still have to multiply all of this by this term. So don't mess that up. Because that's the same thing as saying this term, let's say it's 100 minus x, or 100 minus y, and then we have, this is to the 1/2 power, that's the same thing as square root, and then we square it. We still have this same bracket here, 100 minus y to the 1 power, but it still becomes a product. You're still having a product, this multiplied by y squared, so don't mess that up. And I guess we'll just rewrite it. So we have y squared, 100 minus 2y squared plus 10 squared. Alright, hell yeah. And then we're going to divide by 102y. Cool, and that's going to equal this, 5 minus x squared plus y squared. So the next thing we do is we're trying to get x by itself, so we need to subtract y squared. So let's do that. So let's just let's do minus y squared right here. The only way that we can actually add these is if this has a denominator that's the same. And the only way to get a denominator down here is to multiply the same thing by the numerator. So I'm going to be 100 minus 2y, and then 100 minus 2y. And then let's get that negative back. Cool. So now I can add these. And we can do that same thing. I see oranges and oranges. You know what I mean? So cool. Let's factor that out. So I have, and like here, this is a negative. I don't know. This is the same thing as -1. A -1 producted into this. So why not just say this is, and we'll do this in 2 steps. So that's going to be -100 plus 2y. But even like right here, maybe this isn't a nice way to write it, so you can write 2y minus 100. So this whole thing is just 2y minus 100 times y squared. Alright, so now if I'm doing the orange thing or factoring out this y squared, I'm going to have 2y minus 100 plus, since I have a plus here, it's just these terms, so that kind of is nice. 100 2y squared plus, 10 squared. Cool. So I just added those. I feel like I wasn't supposed to do that. What am I supposed to do? Yeah, let's take a look at this. Because, I mean, we have to that's the thing of just like, well, maybe I just overly complexed it. Because if I did this, this is still just divided by 100 minus 2y. And I can't really... what up? Alright, hell yeah. So I see where I went wrong, and I might just kind of redo this one. But it was kind of up here. Anytime you got a couple things going on, and then you can just kind of divide by the denominator and kind of separate terms, that's always a good thing. So we're gonna do that. We're gonna redo this one. So this 2 will cancel one of these 2's. This half will cancel that 2, and we still have this -1. This is going to be y divided by that square root, and this is going to have our x term. This is going to equal, over here we have that 102y divided by a bigger square root, and this is just my y term. Okay, so we need to get this term up top, so we're going to have the square root of this x term up there. Over here we're going to have y, the bigger square root, and then 102y. Okay, hell yeah. And now I'm going to square this side. So now that's where we're at. And well, if we square both sides, this is going to be 5 minus x squared plus y squared. So then when we do that, we can subtract y. So there we go. So we're going to do minus y squared plus, so now we have this side. This is going to be, and we squared this side, so we have y squared multiplied by this thing, which is 102y squared plus 10 squared. And we got rid of the square root because we squared this side, so we squared all of this. Okay, so now that is going to be divided by 100 minus 2y squared. So now what we're going to do is we have a denominator, but we have 2 terms up here. I mean, we could factor this through, or we could... oh, and that's the other okay, I'm going to bring up a mathematical thing, because it's just like, well, do we need to put this denominator under both of these things? And the answer is no. Let's just pick a number for this. Let's say this is 2, and then we have 3 plus 4. And then I'm going to divide it by 2. So if I take this 2 and put it under the 3, like that jives. You know what I mean? Because I could say, and then obviously the answer is going to be 7, so let's see if we get there. But I could say this is just 2 times 3 divided by 2 plus 4 divided by 2. Okay, so if this is 3 divided by 2 plus 4 divided by 2, that's going to be 7 divided by 2, and then we multiply by 2. What we don't do is this. We don't say this is 2 divided by 2, 3 divided by 2 plus 4 divided by 2. And so that's the thing when it comes to mathematical concepts. It's just like, well, maybe I don't see, like I get to here and it's just like, well, I have a denominator and I know I have to like factor that in, but I don't want to. Like right now I don't want to factor this in, but I want to put this under a couple terms. And so so that's what we're going to do. I'm going to put this under both of those terms, and I just kind of prove that to myself. So I like doing that stuff where it's just like things aren't so obvious, but now we're going to do that. So we have negative y plus y squared, because these were the oranges I was talking about, and I don't want to lose that relationship. So now we have this is going to be, so this term in here is going to be 100 2y squared, and then we're going to divide it by the denominator, 100 2y squared. And then we're going to have 10 squared divided by the denominator, 100 minus 2y squared. Okay, and you should easily see that this is 1. I don't know. A lot of this stuff isn't like, ooh, you know, now you should see it or whatever, but it's just grueling just knowing that these things pop up all the time, and then you're going to try to look for them. But like I said, at the end of the day, I didn't really care. It's just like, let's just get a monster nasty equation in terms of what are we trying to solve? We're trying to solve for x. You know, even back here, I have 5 minus x squared plus y squared, and I got the y squared to the other side. So this thing is still equal to 5 minus x squared. And we're still trying to get all of this stuff in like x in terms of y. But like right now, I can see this is 1. So this is going to be negative y squared plus y squared, but it's going to be a product of this. So now let's FOIL it in. So we have negative y squared plus y squared plus 10 squared 100 minus 2y squared. These cancel, and now we just have this, 5 minus x squared. We need to take the square root. So the square root of this, if I just did that, is the same thing as square rooting the top, square rooting the bottom, and we can easily do that. So we have 10 divided by 100 minus 2y is equal to 5 minus x. So now we're getting places, and now we just have to get this x by itself. One way is to add it to the other side. That's going to be x plus this, and let's subtract this over here. So we're going to have x is equal to 5 minus 10 divided by 100 minus 2y. And the only way I would actually do anything like this, you know, when the math kind of gets complex, is to know kind of what the answer is to begin with. And we, you know, and some might say it's just like, well, you don't know what the answer would be. It's like, hell yeah, we do, because we know that this hard type of math isn't the only way to get answers. And you know, just approximating, getting close, we know that y is, you know, I even did it in the videos, like y was for sure 24.5, x was 0.196. So those are the values we should get. So let's, in our calculator, alpha y is, well, 24.5. And we'll use this equation, 5 minus 10 divided by 100 minus 2y. And we get the wrong answer. Damn it. Are you sure? Oh, that's a bummer. Yeah, we messed up somewhere. All right, hell yeah. So, like, what do? You know what I mean? I don't think it's due to my, like, well, I don't know. Yeah, if you write cleaner, but there is a speed that you want to write that's going to be efficient. So I guess we're just going to do this one again. So I can I can cancel out 2's from both sides. This half cancels that. This is a -1. When I get this over here, that -1 goes away. We're going to have y, and then we have the square root 5 minus x squared plus y squared. Yeah, and maybe I can write a little bit sloppy, but still like kind of hold it together. You know what I mean? Cool. So now I have this 100 minus 2y squared plus 10 squared. Alright, so I'm trying to solve for this x. So now I know I need to get it up there. And I need to get this up there and this down there. But I'm going to put x on this side. Sometimes mentally that is kind of just a little bit nicer because we're probably used to that. Alright, if this term has the x in it, it's on this side, then over there I have y, and then the square root 100 minus 2y squared plus 10 squared, and then divided by 100 minus 2y. Alright, so now I'm going to square both sides. So I'm going to have 5 minus x squared over here plus y squared. I swear it's just like, I bet you I was just off by like maybe like right here I messed up. It's kind of fascinating where you're just like, where did you think you messed up? I think oh man, this is tricky. I think I got here. This was 5 minus x. So I added the x over there, and then I subtracted this. No, that's, anyway. Alright. So I have this side, we squared everything. So I'm going to have this side, and this is going to be y squared, and then we have 100 minus 2y squared plus 10 squared. Divided by 100 minus 2y. Cool. I'm going to factor this in. And, oh yeah, this is probably, yep. I just had a 10, no. If I squared this side, this is squared, yeah, so there you go. So yeah, I don't want to make more mistakes. Okay, but yeah, let's factor this through. This is going to be y squared plus 10 squared y squared divided by 100 minus 2y squared. So I'm satisfied with that. I brought the y in here and then the y here. And then I divided this by the same thing, so this just becomes y squared. Now we're going to subtract y squared. Those go away. Oh, so there you go. I still had a 10 squared. No. Because now we're going to take the square root. So these y squareds go away. Now we're going to take the square root. So I'm going to have 5 minus x. I don't know where I'm making my mistake. But then we're taking the square root of this. It's going to be 10y. And then we have 100 minus 2y. Okay, and we're trying to solve for x. Man, I just don't know why it would look any different. Or like where, oh, there you go. So this has to be 10y. So holy, I lost a y. So why did I, yeah, so this was, yeah, so there you go. So I lost a y. So right here, when I factored this in, this should have a y squared on it. And I just didn't do that. So I should have a y squared up here, and then I'm taking the square root of all these terms. Whew, but that's brutal. You know, it's like I definitely show you the brutalness, and yeah, it's just really easy to lose a term like that. So my take-home point is like kind of already have the answer in your head, and every step that you do that kind of got a little bit out of hand, you know what I mean? It's a little bit much. Throw that into your calculator. So coming back to here, let's get the x over here. And then we're going to subtract that over there. So we're going to have x is equal to 5 minus 10y, 100 minus 2y. And now this should work out. So we have 5 minus 10y divided by 100 minus 2y. Okay, hell yeah, and we get that 0.196. Nice. So that was brutal, but we have two equations. We have, back to this one, if we throw in, and I'm going to store that as x, if we now do 5 minus x divided by x, we get 24.5. So we figured out the answer. We have optimized the answer. So we have these two equations. One says x is this, and the other says y is this. So let's get a fresh sheet of paper, and we're going to write these equations. Y is equal to 5 minus x divided by x, and then we have our other equation that says x is 5 minus 10y, 100 minus 2y. All right, so cool. So we have two equations, and we have two unknowns. So one way to solve this system of equations is to, this is in terms of y, so just plug this into there, and then we can solve for x. Which one do I want to do first? I don't know. All right, I'll do the one that I don't think I've done, where I want to know y. So if I want to know what y is, I have to use this value of x and then throw this into these two x's. So then I'll have an equation with just y in it, and then I can solve for y. So I have y is equal to 5, and then what's negative? This is just negative x, so let's write that. So negative x is just the same thing as negative 1 times x. This is x. What if I multiplied by a negative 1? I'd have to put a negative 1 here, and then I would have a negative 1 here. And a negative sign is also, anytime you get a negative sign, just make it a positive, and then just multiply by a negative 1 to the next term. So hey, a negative times a negative, this goes away. And, well, that was kind of hella confusing. But, and I probably shouldn't have ruined this x term. So we had x is 5 minus 10y divided by 100 minus 2y. But yeah, a negative x is going to be negative 5 plus, or it's going to be 10y, 102y minus 5. So, a lot of times people will, if I'm factoring in a negative 1, this is my negative, this becomes positive, put the positive first, the negative second. I know that's just kind of a custom. All right, so we have 5. And now instead of 5 minus x, I can say this is y is equal to 5 plus negative x. And we just solved for negative x, and negatives are my nemesis, so I think that's kind of a pretty slick way to do it. But you can still get kind of confused. But no, I'm going to do 5 plus, and then this, what's my negative x term? My negative x term is this. Hell yeah. So we're good. We're going to do 10y divided by 100 minus 2y minus 5. So the 5's cancel. So I'm pretty set there. But all right, so what I'm doing is I'm putting this term into these x's. So I've just put it into this x, that's all I've done. Now this whole thing has to be divided by this term, which is 5 minus, and I could just write it, but I could do an extra step right now. I have two things that are, anytime I see the negative sign, I hate negatives, I'm just going to call this addition. So I'm adding these two terms, even though even though we have a negative or a subtraction, this is still the same thing as 5 minus. No, it's 5 plus the, this term to the negative 1. So I think in a lot of videos, I'm just going to keep saying I'm adding these because it helps me out, I think. Okay, so I'm adding these two terms. I can only add them if the denominators are the same. So to get this denominator, I have to multiply top and bottom by this 100 minus 2y. So I'm going to, on the top, I'm going to have, and let's just do this in one go. I'm going to have 500 minus 10y, and then I'm going to subtract 10y, and then the denominator is the same. So I'm going to have 500 minus 20y. Sorry to do this just over here, but that's might as well. So there you go. Did a couple steps. 500 minus 20y, and we still have to divide by that denominator, 2y. Okay, and now right here, dividing by a fraction is the same thing as multiplying by the reciprocal. These 5's cancel, so I'm going to have this fraction multiplied by the reciprocal of this fraction. So I'm going to have 10y, 102y, and I'm going to multiply it by the reciprocal. 102y, 500 minus 20y. Alright, booyah. So now I can just FOIL this in. I have 1000y minus 20y squared. Is this what I want to do? Sure. And then down here, I have, I swear this is wrong. No, I just haven't done this one. Yeah, the numbers are just a little bit bigger than I'm used to. So I have 1 times 5 is 5, and I got 4 zeros. 50,000. Now I'm having negative 2,000y. So I like to say, like, just pick out the first digit. So this is 2. 1 times 2 is 2. And then just add, so 2 plus the 3 zeros. So 2,000y. So that's this, that. Now we do this. 2 times 5 is 10, plus 2 extra zeros. So that's going to be 1,000. So minus 1,000y. And then we have 2 times 2 is 4, so we have 40. Negatives are going to be positive 40y squared. Positive 40y squared. Alright, so this becomes negative 3,000y. And we have the top. So we still have a denominator, we have a numerator, but it's still equal to y. So now we're going to take this and get it up there. So we're going to have to take this 5,000, so we have 50,000y minus 3,000y squared. There's no way this should be no, we're not going to have a cubic equation, because I think I could have canceled out a y a long time ago. Anyway, maybe not. So we have, and then we got this plus 40y cubed. That's going to equal 1,000y minus 20y squared. It's going to equal that numerator. So we took the denominator and brought it upstairs to over there. Alright, so now we can just totally cancel out a y. So I'm going to do that right now. This is 50,000 minus 3,000y plus 40y squared is equal to 1,000 minus 20y. And now let's get, we're just trying to get something like y squared plus y plus a constant is equal to 0. So this looks pretty good. So we're going to do 40y squared minus 3,000y plus 20. So we're going to have 2,000, like 2980? 2980? Because 2980 plus 2 is going to be 3,000, right? Okay, so we have minus 2,980y. 50,000 minus 1,000. That's going to be 49. So we have plus 49,000 is equal to 0. Okay, sweet. And I'm going to use one of those tricks today where I just said, hey, if I have 2a plus, 4b plus 8c is equal to 0, hell yeah, that's the same thing as 8 plus 2b plus 4c. I just factored out a 2. I'm going to do that. I'm going to factor out a 0 right here. So this is the same thing as 4y squared plus 298y plus 4,900 is equal to 0. And might as well go another step, 298. I'm going to try to not use my calculator. I know what 300 divided by 2 is. That's 150. So this is going to be 149. Alright, so let's do it one more time. So we got 2y squared plus 149y plus this is going to be, well, I don't know, 5,000 divided by 2 is 2,500. But it was going to be 100 less, so this is 2,400. And is that right? No, hell no. It's 2,450. Oh, yeah. So it was 2,500 but we were off by 100, and we divided that 100 by 2, so we get 50. So it's 2,450. So we got 2,450 is equal to 0. All right, sweet. So now I'm going to start to do the, kind of rewrite this. 2y squared plus 149y plus 2,450. All right, hell yeah. So back at it. And I refuse to use the quadratic equation. I always complete the square. So we can't, but what we're going to do is we're going to get this by itself. So this has to be 149 divided by 2y. And then we have, we need to get this to the other side. So we have 2,000. We can divide that by 2, though. How would we do that? I think I'm just going to use long division. So 1, 2, this is 2, 5. So we have, so over here we have 1,225. But see how like math is so tricky, because you just have to do like every step right, and then if you don't, you got to go find your errors. Okay, so I have this isolated. I got this to the other side. See, I'm already making mistakes because it's got to be negative. I do this pretty fast, and so I'm just going to do the fast method. I know that I have to get y plus half of this. So that's going to be 149 divided by 4. And if I do that, I'm going to have to add this term. This is the only, this term squared is the only term that I don't have over here. I do have the other terms, the other two terms. So I need to add this term on both sides. It's already added on this side when I put it into this little squared equation. But I don't have it over here. So I have 149 squared divided by, for now I'm just going to call this 4 squared. Sometimes I can cancel stuff, but probably not. Alright, so then I have this. I'm going to take the square root of both sides. And once I do that, then I just have to subtract 149 divided by 4. Cool. Now this is where you would do the traditional quadratic equation. To get this, we're going to use all the same methods. I can't add these unless the denominators are the same. So I'm going to put a 4 squared here, and then a 4 squared up top. And I don't know if I oh man, I mean, should I do this without a cal? I don't really want to. Yeah, I'm going to throw in the towel on this one. So we're just going to get a number. I'm just looking for integers here, but we have negative 1225 times 16, and then we're going to add it to 149 squared. Sweet. So up top I get 2,601. Don't forget your plus or minus over here. That's going to come in handy. And then this is going to be divided by, I'm just going to do the 16 for now. So now we have this. So we have plus or minus, and then we got minus 149 divided by 4. Oh, yeah, no duh. I still shouldn't have done that, because obviously this is plus or minus the square root of, if I can take the square root of the top, square root of the bottom, that's the same thing. And so the square root of the bottom is 4. And so now I can add these two things together. I still don't know whether I have the negative or positive, so let's find that out right now. And what are we solving for? This whole thing is solving for what y is. Y should be 24.5. So I'm going to take the square root of 2,601, divide it by 4. I'm going to store that as x right now. And then we're going to subtract 149 divided by 4. That gives me negative 24.9. So let's do negative x. Yeah, let's do this and then negative x. Whoa. Where did I go wrong somewhere? Oh, this is bumming me out. Oh yeah, and then this is the other thing when math, you know what I mean? I don't know. Like I can't not make mistakes. So just throw this into your calculator. 2x squared plus 140, because we might have already made a mistake, just a little sign error, plus 2450. And then we're going to graph this. We're trying to get 24.5. Does it even cross? No, and so this equation is wrong. So we need to go back to we need to go back here because we're not even there's no reason to continue if like you already made an error. So this shows you that we already made an error somewhere in here. It's probably this negative. You know what I mean? How did I get well, let's see what we did. Yeah, so we went from negative 2,980y, and then we just changed it to a positive. So it's kind of fascinating that even you watching these videos can be like, whoa, saw that one. And sometimes I do rewatch my videos, and so because then I can kind of learn how to be, and just get slightly better in some different ways. All right, so yeah, and I do recall that from the other problems that, yeah, you had a negative here. It doesn't really change a lot, except that we still need to add this this term on both sides before we square, so that's still that term still jives. But now when we do this, instead of subtracting over here, we're going to be adding this. So that is the only difference. So that's kind of cool when you make mistakes to go back and be like, whoa, all we had to do was just that a couple times, and it was a negative. You know what I mean? It's always a negative. Okay, so now we're going to do this, and I'm going to do minus the square root 2601. Especially if you're writing this in, it's always just easier to do the negative root first, because then you can go back in your calculator and change it to the positive. Okay, so it's the negative root that I want anyway. So now I'm going to say y is equal to, and I'm going to have the negative of this. I can add these two numbers because the denominators are the same. This one's negative, this one's positive, so I'm going to put this one out front. 149 minus the square root 2601 divided by 4. And so now we have an equation for y. Whoops, damn it. Hell yeah, you know what I mean? We did it. So that was pretty cool. Now in another video, probably not anytime soon, I don't think, I'm going to do this whole problem in terms of a rectangular box of any dimension, where you can, well, there's a few things going on here. You know what I mean? One is like, hey, have, if you're going to choose any location on this wall, have an XY coordinate on this wall. So this would be x1, this would be x. Well, I don't know how. Oh, this is interesting. Like for this problem, you have to mirror. This is a mirrored problem. That's why we only have two variables. So that's another interesting thing about these problems. Is sorry, I'm pulling up this kind of squattier box, but it's the same dimensions. Is that we said the fly was 1 meter up midway on that wall, midway on this wall 1 meter up. Because it's going to be symmetric on both sides, you're going to take the shortest route is going to be the same over here to the halfway point as it is over here. And so you only have these two variables. That's why you only have two differential equations. But I guess what I'm getting at is I could still have an input of any location on this wall. I mean, it could be over here. And then, well, I don't know. Yeah, that's interesting. I guess, yeah. No, I'm sure the equations, even if I'm at the midpoint or past the midpoint, the equations are just going to flip over. So I don't think it would make any difference because the box is symmetrical as well. Okay, sweet. So yeah, I guess what I'm getting at is that, yeah, you could choose hopefully any location. And that's also not true, because the way this problem is laid out, when the box folds out, I think there are solutions where there's locations that don't make straight lines to this over here. So I'd have to look at that. So as is, if this is 1 meter up on whatever dimension box, and this is 1 meter up on a box that has more than length of 1 all around, I could have this width, be a width W, a height H, and a depth, or what's the other dimension? Width, height, oh yeah, and a length. So then I could have L, H, and W. And I should be able to set up my partial differentiation equations in terms of LHW, and then get a solution for y in terms of numbers, integers, and an L and an H and a W. So that's kind of cool. I kind of want to do that. You know what I mean? That's a good process to go through. One, go through with the numbers, and then go put back, put symbols back in. All right, so now we are going to do it one more way. All right, hell yeah. So now we're going to solve for the x term. So we solve for y. All right, and so, and then even just right here, maybe I wrote them wrong. So people say stay away from your calculator, but man, the math can get so complicated. It's just nice to know that you're on the right track at all times. So we have alpha y is, well, 24.5 stored as alpha y. This is 5 minus, oh, never mind. So 0.196 stored as x. This is going to be 5 minus x divided by x, so that checks out. This one's going to be 5 minus 10y divided by 100 minus 2y. And so that checks out, 0.196. Okay, so now what we want to do is we want to get an equation that says x is something something y. No, just x is a number. That's what we're trying. We're trying to get x is just an integer, or the same thing that we did for y. So we need to get x all by itself, and the easiest way to do that is to take this equation, and then everywhere we see a y, throw in this this equation. So, all right, so we have x is equal to 5 minus, so now we have 10 times this equation. So even from a mathematical perspective, do you multiply the 10 on top and bottom? You know what I mean? No, because that would just be 1. So it's kind of nice to even just talk your way through that, because sometimes it's just like, oh, because I just want to multiply this equation by 10. So yeah, it's just going to be the top. It's just going to be the numerator times 10. And you could think of that as 10. Any number, you just put a 1 underneath it, and then you got a fraction. So now we have 10 divided by 1 is now multiplying into 5 minus x times x. So now, yeah, multiplication is pretty cool with fractions. Numerators multiply, denominators multiply. Okay, but let's do this all in one go. So 10 times this is going to be, oh man, yeah. So, and I guess, yeah, it's going to be, and I got to think of this as still just a positive 10. You know what I mean? So I'm just going to cover up the negative, and we have 10 times this. That's going to be 50 minus 10x. So we have 50 minus 10x. And then we divide that by x. And that's what we had right there. Cool. And then we'll have to go through and then maybe factor this negative in if we want to do that. Now the bottom is another term. Wait, where are we at? Oh, we were over here. Anyway. Yeah, sorry about that. I didn't even know where we were. So yeah, so we have 5 minus, this was 10y. So that we just did it. This is now 10y. And we're going to divide it by 100 minus 2y. So 2 times this is going to be 10 minus, yeah, and I got to cover up the negative sign. What's 2y? That's going to be 10 minus 2x divided by x. Okay, hell yeah. So now, so this is its own fraction. And these two terms, I can't add them together unless I multiply top and bottom by x. Now I can. And just be cautious, because this is a minus. This is going to be 100x plus 2x, because this negative makes that, you got to think of this as adding and then multiplying a negative 1 through here. So this becomes negative 10 plus 2x. So now you can add. So we would have 98x minus 10. and that's going to be divided by x. Up here, kind of same, well, no, we're good here. We just have one thing in the, yep. So we just have this 50 minus 10x. So we have this fraction divided by this fraction. Same thing as multiplying by the inverse. So this will stay downstairs. And the other thing, if you're just dividing, so if I'm just taking this and dividing it by a fraction, the first thing that pops up is what you're dividing. You know what I mean? And then the numerator pops upstairs. So the numerator x will cancel that x. But yeah, you're basically just taking 50 minus 10x divided by 98 minus 10x. All right, so let's rewrite that. X is equal to 5 minus 50 minus 10x divided by 98 minus 10. Cool. All right, so now we can, let's take this 5 to the other side, but actually we want to kind of take, or what do we want to do? Oh, yeah, again, we have a fraction. We want to make the numerator the same. That's one thing that we could do. So we could multiply top and bottom by 5 and then start adding these things. Cool, let's do that. So we have x is equal to, so top and bottom by 98. And where did I lose the x right there? Sorry about that. So top and bottom by 98 minus 10. So we have 5 times 98x minus 10. So that's going to be 98 times 5. 45, 49. Is that about right? 490? Yeah, because 2 minus, yeah, so 490. So this is going to be 490x minus 50 divided by 98x minus 10. And now we're subtracting. I'm just gonna do an add the opposite. So we have to add negative 50 plus 10x. So now figure out which way you want to do it, but there you go. So now we have 490 plus 10x, so that's 500x minus 100 divided by 98x minus 10. This is still equal to x. Now we can bring this up here. So that's going to be 98x squared minus 10x is equal to 500x minus 100. Now we want to get something like x squared plus x plus a constant is equal to 0. So we're going to keep this 98x squared over here. We're going to get this over here. That's going to be minus 510x plus 100. And even right here, it's just like I want to know if I made a mistake. Probably did. So might as well just throw in the towel instead of trying to figure out if we did it right. And our x should be going through 0.196. And it looks like it's pretty good. No, so this is wrong. It says my x is going through 0.204. And that was the whole point of doing this video, is like, hey, let's make some errors and see if we can find them. I think we got a little out of control on this one, so let's redo it. Alright, I think my negative game is just it messes with me, because it's just, I don't know, anyway. So, we're trying to solve for x. Anywhere where we see a y, we're going to throw this in. So let's just do this over here. So if I have 10y, that's going to be 50 minus 10x divided by x. Cool. If I have 2y, I'm still going to do that. 2y is equal to 10 minus 2x divided by x. Cool. So now this says x is equal to 5 minus 50 minus 10x divided by x. And even just right now, well, no. We have to do divided by 100 minus this. So we have minus 10 minus 2x divided by x. I need to do that, x top and bottom. I'm going to have 100x plus 2. Oh, so that's where I went wrong. So it's going to be 100x plus 2. I'm going to have 102x. And yeah, I've done this problem before. So there you go. I found my error. I'm going to come back here. And right here where I had 100x plus, yeah, so this -1 is so bizarre that I had this -1 here. And then factored it through, but did not, I didn't do -10 plus 2x or whatever. Yeah, I did it over here, but yeah, so my negative game is just awful. Cool. But there you go, 102x minus, yeah, so I think we're good. And so this should be 102. And now let's double check the answer. Nope, that's still wrong. So okay, so let's still continue because I'm sure that messed up a few things. All right, so here on this denominator, we're going to have 102x minus 10, and we're still dividing by x. Okay, so now we're going to have top and bottom. So this whole thing becomes 5 minus, top stays the same. Bottom is this, 102x minus 10. This is all equal to x. So we have this equation right here. I need to get, yeah, I guess I'm going to get this denominator the same. So I'm going to have 100 and, oh yeah, so yeah, we're going to, yeah, for sure, this 102, it needs to be multiplied by 5. So we're going to have 102 times 5. Is 10, is 5, oof, no. 102 times 5. I should just be able to do this in my head. 102 times 10 is 1020, divided by 2. That's going to be 1,000, divided by 2 is 500, it's 510. Alright, final answer. So yes, but I'm going to have this denominator, top and bottom. So when I FOIL this through, I'm going to have 510. Oh yeah, I should have just saw that. Yeah, it's good to not use your calculator. Okay, so minus 50 divided by 102x minus 10. And now I can subtract this. 50 minus 10x, 102x minus 10. So I guess I don't mind negatives. I just do this. 510 minus, it looks like I'm adding 10. So it's going to be 520x, negative 50 minus 50, so minus 100, divided by 102x minus 10. Cool. Now this is just equal to x. So now I'm going to have 102x squared minus 10x is equal to 520x minus 100. So get this over here, 102x squared. I have negative 10. I'm going to subtract 100. So I'm going to have minus 530x is equal, no, plus 100 is equal to 0. Alright, so now I should have the right answer. But yeah, it's good to have a calculator to kind of double check, especially a graphing calculator, because yeah, we made one error, but we didn't realize that error carried all the way through. Alright, get that 0 value. Perfect. And so we have our x, 0.196. Okay, so now what we're going to do is let's take this value, 102x squared minus 530x plus 100 is equal to 0, and we're going to complete the square. Is there anything that we can... Alright, so this is going to be 51x squared minus, this would be 250 plus 15, 265, minus 265x plus 50. So I just divided everything by 2. I can't factor anymore. So now I'm going to get x squared minus 265 divided by 51 plus 50 divided by... Whoa. Just get this the hell over to the other side. So minus 50 divided by 51. And then I'm going to complete the square. That means I'm going to have... well, I guess let's do it. So I'm going to have this term but divided by 2. So I'm going to have 2 times 51. And I guess I could just do this, 102 right now. And then I'm going to have to add 265 squared divided by 102 squared. So I'm going to square this term when I do this, and I don't have that in completing the square. So I'm going to add that to that side. Okay, so now I'm going to take the square root. We're going to have a plus or minus, and then I have to add 265 by 102. Cool. So I have to get, if I'm going to add these two things together, I got to get the denominators. Oh man, I feel like I messed up. I guess I didn't though. Oof, yeah, I just have to get the denominators to be the same on both of those. So I'm going to have negative 50 times 102 squared divided by 51 times 102 squared. Alright. And then I'm going to add it to 265 squared times 51 times 51 times 102 squared. Alright, so the denominator is the same. Now I can add the numerators. And again, I'm going to throw in the towel on just getting a number for this. So we got negative 50 times 102 squared plus 265 squared times 51. So I have 3,061,275 divided by 51,102 squared. And cool. Can I divide this by 51? Yes, I can. So there you go. Holy Toledo. So this is the same thing as I'm sure there was probably a cleaner way to do that. But we have 102 squared. And this is under the square root. We're adding 265, 102. So I see this 102. This thing is the same thing as square rooting that, square rooting that. So now my denominators are the same now. I can add these two. I don't know if this is plus or minus. So let's find that out right now. So we have minus the square root 60025 plus 265. I guess it's all divided by 102. And we get 0.196. So yeah, the negative root applies, and we have x is negative square root 60025 plus 265, all divided by 102. Hell yeah. I don't know, this was satisfying now, because we had two differential equations, you know, kind of back to the beginning. We had these, partial differential equations that we had to set equal to each other, or we set them both equal to 0, but then we solve for, it's a system of equations. They both have a x and a y, and, you know what I mean? One is optimized given, like this is optimized given any y. But that y might not optimize this one. This one is optimized given any x. But just any random x isn't optimizing, any random x might not optimize this. So optimizing them both is setting both these equations equal to, solving for them. We have this equation equal to 0, this equation, and we're solving for the x and y that makes both these equations equal to 0. Because I could get one of these equal to 0 and then throw the other value into there, and this one ain't 0. So, and hell yeah. So we got both. I'm gonna write them out. All right, hell yeah. So we have our two equations for x and y, and this is when that problem is going to be optimized. And this is pretty sweet because I just chose this problem myself. So let's pull up a sheet of paper where we actually show it. Yeah, hell yeah. So this was, I kind of pulled a picture, but I definitely changed the dimensions. Yeah, this kind of, I just wanted to do 10 and 10 and 100. I just thought that was kind of, you know, something I could keep my mind around instead of saying this is like 24 and this is 12 or, you know, some nonsense. And so, yeah, and for sure, and this is kind of the second video on it. Like I said, it'd be kind of cool to go through and then throw some parameters in where you just say, hey, this is any side with a height, width, and length. That would be pretty sweet. And then maybe any location on here, an X and a Y location, and then mirrored over here from an X and Y location. You know what I mean? So it'd be like, hey, if the spider saw the fly right there, the spider is going to be like, hey, go to the very opposite side, kind of trick the fly out. The fly thinks it's like the farthest away from the room, but then, hell yeah, a spider's going to kick into gear and kind of take the, you know, the most efficient route towards that fly. And sweet. And it was just kind of cool because that's the other thing. It's just like, was this worth it? Not really. You know what I mean? We got two equations that are with integers, and that's a good skill to have. But there's nothing extra here. Like, these two solutions just satisfy a box that's 10 by 10 by 100. So that's what I'm saying is just like, and this is where people online are just like always like, hey, you should solve these with variables. You know, just make everything a variable. But then, yeah, so how does that work? When we take our partial with respect to, you know, we'll have x and y, and we take that with respect to x, and then partial with respect to y. But you're saying I'm having a length that's with respect to x, y, also width, height, and length? Well, yeah, but those are inputs. Once you input those become constants. And so because they're constants, when it comes to differentiation, all the same rules apply, and you're going to get this same answer. So yeah, when you throw in these, and it's going to be just as simple to do. When you do your differential equations, you'll just regard these as constants. When it comes to adding the fractions, hell yeah, it'll be a lot more complicated. So I'm excited to actually do that. That'll be the next problem that I do. And I don't know. Yeah. This like this one was too brutal for me. So like I have to be cautious about losing my voice. There's no reason to you know, just go too hard when I could just show you the solution. But it's kind of nice to actually, hey, this is the process I go through. It sucks. You make errors. You find errors. You go back. It's a combination of like, you know, maybe writing sloppy, maybe writing not. Trying to do things like today we did things of like, hey, if I have an equation that's y is equal to, maybe this is the shorter square root plus, you know, something like that. This is the longer. And then, you know, just visually I can be like, okay, my x is there, so hell yeah. So I'm going to get this x is equal to this divided by this y. You know, maybe stuff like that's very helpful. And then I can say I'm going to square this and then, you know, just square those. So doing things that require less writing, I think is helpful in the end. Because there's only so much, like I do a lot of writing, but I definitely pay for it. And at some point, there might be days where I can't write for a while because of, you know, I mean, just wrists and carpal tunnel and stuff like that. So anyway, but I do enjoy doing it. So it's kind of a nice little balance between what I'm interested in putting out and what makes actual sense. But hell yeah. So the fly and spider problem. So thanks for joining me on this one, and that's a video.